when they're sick or they need some financial help. So happy Youth Day to everyone on the call. For those of you that still identify as a youth. But yes, I'm happy to run this call. Obi, we've got Professor Aldous coming on, and we might have Dr. David Scheim and Barry and Jerome Dances joining us from MIT in Boston or wherever they are, Massachusetts. So I'm worried about time. I pre-recorded the session, so I'm going to run a couple of slides, and I think let's minimize the introductions. I will run the slides, my slides first, which is a brief introduction on statistical significance versus clinical significance. And then Zachary will start the recording, where you should be live streaming on YouTube already. I'm not involved with the technology, thank heavens. And then at the end of it, we will cut the session with the cutting of the recording, and we'll bring Prof. Aldous on, and then we'll have a panel discussion with Newton and Colleen regarding any questions on p-values and other mathematical mysteries in statistics.
Excellent. Excellent.
Right. Okay, got 2 minutes to go. 1 minute to go.
Another minute to go. Colleagues who are in the session, if you can please refer to the chat in the meantime before we start. There is a link in the chat. Please complete that in the interim. We will relay that again once the session starts. Xavier, in the meantime, if you can share our opening sequence, and then Dr. Jackie will then start.
No, Obi, it's 18:30, and we're running on Namibian German time. So welcome to the session of Intellectus Campus, everyone. Tonight we are doing the first of a series in mathematics in medicine. We're going to focus on the p-value today. I think a lot of people who are in the clinical world will face people who will discuss the fact that the p-value. So people will discuss that the p-value shows no statistical significance, or they'll say the sample size was too low, or they will say that the confidence intervals were not reliable. And for people like me who hate statistics with a passion, and I'm sorry about that, Newton, but I've always hated stats, I don't have a leg to stand on because I don't understand the p-value to the extent that they do, and they can usually argue with words I don't understand. So this session is designed, first of all, to show every clinician on this group that they do know what a null hypothesis is, and they do know what an alternative hypothesis is. So I'm going to take you through a clinical scenario to show you how doctors actually reason with logic. And then Newton will take you through the statistical analysis starting at KG1 level and then increasing to advanced level quite quickly so that we don't lose anyone, but ask questions if you don't understand it, because it's critically essential if we're going to go forward with p-values and confidence intervals that we actually understand what exactly they are. So, I'm just trying to get out of something on my screen, which I've just managed to do. So show me the evidence. If I go back, I want to go say that we're going to discuss clinical significance versus statistical significance. And we need to also ask, when does clinical significance override statistical significance? And the answer really is in an emergency situation. When you've got 10 or 15 years to do clinical trials, there's plenty of time to argue about what the p-value is. But when you actually need to do something practical in an emergency setting, then we need to start looking at clinical significance. What does it mean in aviation medicine? If a condition is life, sight, or limb threatening, it is considered a medical emergency. The Helsinki Agreement allows doctors to use new therapeutic measures if they have no other resort and if they believe, according to the doctor's judgment, that it will save life, it will reestablish health, or it will alleviate suffering. And this is the convergence of clinical research with professional conduct. And if the treatment of the sick person requires that the doctor needs to use their judgment using a treatment that offers hope of saving life, reestablishing health, or alleviating suffering, then they may do it. And the thing that this says is it establishes that it is important to get informed consent. So because we are largely clinicians on this group and because we are largely interested in case studies so that we can apply something to it, because personally, if I get a 45-minute didactic lecture, I'm likely to not be paying any attention about 25 minutes into it. I'd like to present a case on the December in 1995 at 4 p.m. in London. And the reason I know it was the 21st of December is that's the winter solstice. And it was snowing outside and it got dark at 3 p.m. and it only got light at 9 a.m. And I wouldn't recommend that to anyone, really. And I saw a 37-year-old HIV positive man from Nigeria. He had a CD4 count of 39, and he was complaining of a few weeks' history of worsening headache, cough, night sweats, fever, loss of weight. But his other concern was that he couldn't swallow, and he was choking when he swallowed, and he'd noticed that he was deaf in his right ear, and he was losing balance, and he had a lot of difficulty with light, and he had a sore neck. So this
My
patient,
apologies, Dr. Jackie. We have commentary that you're not audible.
well, then, as Belle has said, the person has not clicked on their audio. Please, can you put that in the chat? Is Belle on the call?
No, unfortunately, she's not. Okay, kindly
So
proceed.
people need to exit and they need to re-enter and click audio, use computer audio when they re-enter. Can you put that in the chat, Zachary?
Yes.
Great. So I don't have access to the chat, otherwise I can't see my screen. So if we look at the diagnosis of this patient, the null hypothesis, which we're all sort of don't understand, is basically that there is nothing wrong with this man. The alternative hypothesis is this man has TB meningitis involving his cranial nerves, or he has cryptococcal meningitis for those of us that have seen many of these patients. I trained at Groote and I did my intern year at Freya Hospital in the Eastern Cape, and I did my pediatrics at Red Cross Children's Hospital in Cape Town. And I saw hundreds and hundreds and hundreds of TB meningitis patients, and this history is absolutely typical. However, this was the first TB meningitis case that the infection and immunity department at a teaching hospital in London had seen. So I needed to check my hypothesis, the alternative hypothesis, against the null hypothesis. On examination, he had neck stiffness. His optic nerves were normal. He did not have papilledema, indicating there was no raised intracranial pressure. And the investigations, the full blood count was really not very remarkable. Liver functions were, however, raised, and his ESR was well over 100. His chest X-ray showed infiltrates bilaterally. His CT brain was normal. The reason that we did this was to be able to do an LP. This procedure is not always available in an under-resourced setting. And his LP, lumbar puncture, showed high lymphocytes. It showed a very raised protein, and it showed no cryptococcus, and his cryptococcal antigen was negative. So a diagnosis of exclusion in this patient is TB. However, we didn't have proof. And you can't really treat a patient who's got abnormal liver functions with rifampicin, isoniazid, pyrazinamide, and ethambutol without proof. And you definitely in a London teaching hospital. So the instruction was to wait 3 weeks for positive TB culture. But what is the risk of doing nothing? This patient would have ended up with cranial nerve palsies and probably would have been disabled at worst, and at best, he would have been dead. So I needed more evidence. So I jumped on a train and went on the underground to Hackney Central, and I took the sample to a friend of mine who was of Southern African origin, who worked in the lab at the Queen Elizabeth Hospital in Hackney, and I asked them to do a chloride on the sample I had, which I did not mention was cerebrospinal fluid. And the chloride came back at 94, which was low. I do not know why this happens in TB, and I'm sure some clever academic will be able to find out, and it might even be in the literature. But the bottom line was that 30 patients a day in the Eastern Cape have a CSF chloride done. And if it is low, they are commenced on TB treatment. But the problem is that the clinicians are so busy that they're not able to write this sort of thing up, and they don't have the resources financially or in terms of staff. They're 12 interns in a 900-bed hospital. Who's going to write this paper up? So let's look at clinical significance versus statistical significance. In a medical emergency, as we've said, life, sight, or limb-threatening situation, then clinical significance will override. Statisticians are often not aware of the clinical significance. So they don't know if they're doing clinical significance on some obscure part of the clotting profile and clotting pathway, or whether they're dealing with a life or death situation. And the p-value cannot be interpreted without understanding the clinical significance. Clinical significance resides with those who provide expert opinion. And expert opinion is another area of great controversy because academics are put in positions where they are experts. And in a novel situation, they've never seen a single patient with the condition. So I think it's very important to suggest that going forward with disease X or whatever else is going to plague us in the future, that we need collaboration between the frontline observers and the researchers. And with that, I would like you to start playing the recording, Zavary, and I will stop share on my screen. Currently serving as the Deputy Director of Health Research at Zimbabwe's Ministry of Health and Childcare. With over 2 decades of experience, he has significantly advanced healthcare systems in Zimbabwe, coordinating and promoting research across various program areas while focusing on health systems strengthening. Additionally, Newton excels in developing work plans, prioritizing initiatives, and conducting performance appraisals to ensure research sections operate efficiently. He plays a crucial role in drafting collaborative research agreements and previously served as a research scientist at the National Microbiology Reference Laboratory, further solidifying his expertise. So welcome, Newton, and I look forward to your discussion on the p-value. We have mentioned before that statistics are an area that most doctors don't really understand. And then when someone who's good at statistics argues with them and says the sample size is too small or the p-value is insignificant, they don't know how to argue. So I would be very grateful if you would give us the kindergarten version, which I need, of the use of mathematics in medicine. And with that, I will hand the floor over to you. Please unmute your mic.
Thank you very much, Dr. J.K. Stone, for the introductions. I'm going to proceed straight away into the talk of the day, which is use of mathematics in medicine, where specifically I have got this singular honor to talk about p-values and confidence intervals. So this is the outline of my presentations. I'm going to look at the basics, then I will look at the p-values. I will get on to confidence intervals, then I will then conclude. So I'm going to, first of all, look at the basics. We're talking about use of mathematics in medicine. And mathematics, broad as it is, I've just given a presentation there where I'm illustrating the different branches of mathematics, which includes all those, including logic, algebra, set theory, applied mathematics. But today, I'm not going to look at all of those ones in this talk. I'm mainly going to focus my talk on statistics and probability. These are the two areas which I'm going to be focusing on. So for starters, I just wanted to make sure that everyone is on the same level. I'm going to define statistics, which is defined as the science of collecting. We organize the data, summarizing the data, analyzing the data, and drawing conclusions from the data. So statistics, a branch of mathematics, which is very important, is the science where we are doing some studies to collect data, organize the data, summarizing the data, analyzing the data, and drawing conclusions from the data that we have collected. And for the talk tonight, I'm going to be mainly focusing on the last one, which is drawing conclusions from the data that we have collected as we are going through these studies. So I'm going to move to the next section where I'm just focusing on the basics still, where we are looking at the branches of statistics. We have got descriptive statistics and inferential statistics. In this session, I'm not going to focus much on descriptive statistics. I think this is a talk of another day. But today, I'm mainly going to focus on inferential statistics. So just to bring into perspective, descriptive statistics consists of the collection, organization, summarization, and presentation of data. But inferential statistics, this is where we are focusing on generalizing from samples to population. So we are going to gather data from a sample, and we want to use that data to generalize to the population. This is what we are going to be looking at under inferential statistics. And again, let me also indicate that I'm not going to look at everything. This is where p-values and confidence intervals lie. So this is why I have really decided to focus on inferential statistics. And again, I said just to make sure that everyone is brought on board, I want to explain a little bit the idea of statistical inference. Some call it inferential statistics, a branch of statistics. So we have got our population there. It is not possible to start the entire population because of time, energy, and resources. So it may not just be feasible for us to gather all the data about the population. So what we do, we take a sample. A sample is part of the population. And we study that sample. What is important is to make sure that the sample is representative of members of that population. So we study that sample. We come up with conclusions from that sample, which we want to generalize to the population. So the process of now generalizing the findings of a sample to the population, this is what we call the statistical inferences. So there's that term here, which is a hypothesis. This is a guess that we make as we are doing this exercise. So we are going to be meeting this term again, hypothesis. That's a scientific guess that we need to prove by a scientific method. Let me now go to where do we apply inferential statistics or statistical inference. We determine from the sample, we determine the mean. And we want to use that mean to approximate the population mean. we determine the sample proportion, and you want to determine the population proportion. We may want to compare two populations, and it's not possible to start the entire populations. We can take a sample from population A and another sample from population B, and we want to see if there are differences in those two samples, which we can infer to say that the two populations are different. And we can also have the same population that goes through some treatment, and we measure the same population after. So this is a before and after a treatment, and we can try to check if the mean before treatment is different from the mean after the treatment. For example, a population is exposed through some dietary intervention. We want to see if there is if the mean of a biomarker before the treatment is different from the mean after an intervention. We can also do the same with the proportions. We can do a statistical inference on some measures of association. I'm not going to mainly focus on these measures of association in this talk, but just important for us to mention that we can also do statistical inference where we are working on the odds ratios, relative risks. Then we can also look at statistical inference, where we apply it to determine where clinically important difference. I'm going to look at this one later. And what we mean by clinically important difference is determination of the smallest difference considered biologically or clinically relevant. So in order for us to move forward, I will try to again bring everyone on board, just defining some basic some basic terms that we need to understand from the outset. A statistic, for example, we've taken our sample, then we do some measurements, we come up with some calculations. For example, a mean of a sample, that is called a statistic. So a statistic is a figure that is calculated from a sample. If it is calculated from the entire population, it is called a parameter, if we calculate it from the entire population. So what it means is that we can take a sample from a population, we calculate the mean. Then we can take another sample from the same population, we calculate its mean. We take a different sample, another sample again from the same population, we determine its mean. So the range of all possible values of the means that we can determine, they make up what we call the sampling distribution. So they are computed from samples of a given size, randomly drawn from the same population. Let me also highlight some of the few terms. A point estimation is a value that we determine a single value from the sample. For example, we determine the mean, we determine the median, that is the middle value, after we've arranged our numbers in either ascending or descending order. Then we can also look at a change in mean or a change in median. Then we have another term which is different from point estimation. It's called interval estimation. This is where we look at the confidence intervals, the range in which we expect to find the population value, which we said that it is a parameter. Then when we are trying to compare the values of a sample and trying to make some generalizations to the population, we do what is called hypothesis testing. And again, we can also compare two populations to determine if they are different or they are the same. So we come up with what we call hypothesis testing, which is a claim. So with that hypothesis testing, we need to come up with two versions of that claim. The first claim is called the null hypothesis, where we always state that the parameter equals the value specified in the alternative hypothesis. I will explain this a little bit more in the next slides. So I want to bring this into perspective, because hypothesis testing is not something that is out of this world. Hypothesis testing, we do hypothesis testing in the work that we do almost every day. I'll take a very an example which is close to the work that we do every day. A clinical diagnosis is an example of hypothesis testing without the actual use of statistics. I'll touch on the actual use of statistics later. In a clinical diagnosis, a clinician must decide between two hypotheses. The null hypothesis is that the patient has no disease. And in many cases, the null hypothesis is what we hope to refute. So a patient walks into your room, and we hope reject that this person has no disease. So the null hypothesis is that the patient has no disease. And the alternative hypothesis is that the patient has a disease. Now, a clinician does not know which hypothesis is true. They must make a decision on the basis of evidence that is presented. In the language of statistics, clinically diagnosing the patient is called rejecting the null hypothesis in favor of the alternative hypothesis. That is, the clinician is saying that the patient has a disease. So in that case, they are rejecting that the patient has no disease in favor of the alternative claim, alternative guess that the patient has a disease. If the clinician indicates no disease, they are stating that there is not enough evidence to support the alternative hypothesis. What they are saying is that there is not enough evidence to support that there is a disease. So notice that the clinician is not saying that there is no disease, only that there is not enough evidence to support the alternative hypothesis. So that is why we never say that we accept the null hypothesis, although most people in the industry say we accept the null hypothesis, but strictly speaking, we don't really say we accept the null hypothesis. So as we are rejecting or accepting the null hypothesis, there are chances that we can make some errors. The type 1 error occurs when we reject the null hypothesis when it is in fact true. So in our case, we are saying that the null hypothesis states that the individual who comes has no disease, and we reject that the individual has no disease in favor of the alternative hypothesis, which says that the individual has got a disease. So when we reject the null hypothesis, when in fact it is true, we are making a type 1 error. Then type 2 error occurs when we fail to reject a null hypothesis. So in this case, for example, we are failing to reject that the patient who has come has no disease. So that is a type 2 error. So these errors can actually occur in less than 5% of the cases that we see on a day-to-day basis. So presented differently, that's where we are saying a type 1 error is when we reject a null hypothesis which is actually true. So we are making a type 1 error. Then a type 2 error occurs when we fail to reject the null hypothesis, which is false. But when we are rejecting a null hypothesis and that null hypothesis is false, we have made a correct decision. And when we fail to reject the null hypothesis, which is true, then we have made another correct decision. So it's presented differently. So those are the critical steps in hypothesis testing. I thought I just have to quickly go through hypothesis testing because it is related to the issue of p-values as well as confidence intervals. And these are the procedures for hypothesis testing. But let me quickly go to this slide where in our decisions in medical practice, we may want to determine whether means from two populations are different. We may want to determine whether in a population, after coming up with an intervention, we also do some measurements. We want to compare the mean of a parameter before that treatment and after that treatment. For example, we expose the same population, we expose a population, we can determine the mean low density lipoproteins in a population before exposing them to a certain dietary intervention. Then we look at the mean before. Then we expose them to a population, to an intervention. Then after exposing them to that intervention, we also determine the mean LDL, the mean LDL after that intervention. Then we want to determine whether the mean before and the mean after, they are different. Then we can also do the same with the proportions. So in this case, we are saying we have two samples, two sample means of independent populations. We can have two sample means of dependent populations. Dependent populations, this is where we have before and after. So this is the independent samples. So the question to be answered is the difference between sample statistics large enough to conclude that the populations represented by the samples are significantly different? So we want to determine whether the means are different in the two independent populations, or we may want to determine whether the means are different before and after the intervention. We may also want to determine whether there are differences between the mean of a sample and the population from which that sample was drawn. So paired samples are those ones which we said one before an intervention and after an intervention. So in practice, we don't always have to carry out the full hypothesis testing because we now have some statistical tests, some statistical software that can actually do the work on our behalf. We have got statistical packages like Stata, R, SAS, SPSS, Minitab. There are these statistical softwares that can actually calculate for us a value that is called the p-value. So p-values are used in hypothesis testing to help decide whether to reject the null hypothesis or failing to reject the null hypothesis. So we are now getting into the second part, which is the p-values. So by definition, p, that is representing probability. So it is the probability which measures how likely it is that any observed difference between groups is due to chance only. So a p-value of 0.05 or lower is generally considered statistically significant. I'm going to explain this. So what we are saying is that we have got our sample. We calculate the mean. With our mean, we are trying to compare it with the mean of another sample or a population. and we determine, we see that the two means are different. The mean of a sample is slightly or moderately or is very different from the mean of the population. But the decision is that we want to know whether the two means they are very different. But for us to come up with such a decision, we are helped by a p value. It is a probability value. It's just a value, a probability value, which shows us that the differences that we are seeing are likely to be due to chance only. So what does it mean? If the p-value is low, a low p-value, like less than 0.05. Let me give one extreme example. For example, if the p-value is 0, it shows that the probability is 0 that any observed difference between the two groups is due to chance only. So what we are simply saying is that if the probability is 0, there is no probability that what we are seeing, the difference that we are seeing is due to chance only. We are saying the difference really exists, because we can't really say that difference is due to chance only. For example, we are comparing two populations. We've taken a sample from population A and another sample from population B. Then we try to compare the means from the different populations. Then we, after observing that they are different, and we have an accompanying a probability value, a p-value, which is very low. The p-value, which is very low, is simply showing that the difference that we are seeing between population A and population B is showing that the probability is very low, that the observed difference between the two populations is due to chance only. So what we will be concluding is that the difference really exists. It's not just by chance, but the chances are very high that the difference really exists. So the probability is very low that the observed difference between the groups is due to chance only. A low p-value shows that any observed difference between the groups is actually significant. We can't ignore that difference because it's not likely that it's due to chance only. So what it means is that if we had exposed a population A under a certain dietary intervention, population B under another dietary intervention, then we measure the mean low density lipoprotein in population A, then we compare the mean in population B. And we see that the two are different because the probability that the difference is due to chance only is very low. It means that we can't ignore the fact that the two means are different. It's likely that the intervention that we have introduced is contributing to the differences that we are observing. So there is a statistically significant difference between the two groups. Now, what if there is a high p-value? A high p-value shows that the probability is very high that any observed difference between the groups is due to chance only. What does it mean? Let me take one extreme case scenario where the probability is high. Let's say the p-value is 1. What it means is that it shows that the probability is obvious that the observed difference between the two groups is due to chance only. So the probability of 1 is it's obvious. So a high p-value shows that the probability is very high that any observed difference between groups is due to chance only. Let's say the p-value is 0.9999, which is recurring. It's a very high p-value, 0.999 p-value. That 0.999 value, probability value, shows that the probability is very high that what we are observing is due to chance only. So we may not really need to change our medical practice simply because of differences that are due to chance only. So in this case, we are saying a high p-value shows that any observed difference between the two groups is not really significant. There is no difference between the two groups that we are comparing. Let me come to...
Mr. Newton, can I interrupt you there for 1 second?
Oh, yes, yes.
So I've got a question that's come onto the group, and I like to do this in an interactive way because I think the audience are able to engage with us better. So one of the questions is, who decided that P less than 0.05 was significant? And what about a study where the p-value is less than 0.06? Because that's a 94% chance that your intervention is genuinely effective. So why are we not looking at it as a range? So if a p-value is 0.07, technically it's not statistically significant, but there's a 93% chance that this is real that we're seeing. And I wonder if you could comment on question 1, which is who decided on the 0.05, and number 2, whether a p-value of 0.05 to 0.1 is in fact worthy of further study, and whether those groups, you should be looking at the size of the population, because many people will quote a 0.06, but the population groups are not big enough.
Thank you very much, Dr. Jackie, for those 2 questions. I will first of all address the first one. Who decided the 0.05 probability value? This was a generally agreed, a universally agreed value to say about 0.05 will be our cutoff to say this is now statistically significant. Anything above 0.05 will be determined as not statistically significant. Then the second one, please, can you come again for your second one, the second question?
Sorry, I was struggling to unmute there. So the second question is, quite a few studies in the last few years have come up with a p-value, for example, of 0.09. Now, that means there's a 91% chance that this effect is real. And in a life-threatening condition, would you not still need to look at a p-value of 0.09? Because the probability is that this is a real effect, and maybe you didn't have the correct numbers, or maybe there's been some other error along the way. And to discount a study that has a p-value of 0.09 is to throw away very important information sometimes. And we all know, and you and I have discussed this before because I worked in a lab for 2 years, that I've watched that if you drop one case out and bring another case in, you can alter your p-value. So should we be so rigid on the p equals less than 0.05 and say that 0.06 is not statistically significant?
Thank you very much, Dr. Jackie. Thank you very much for that question. You seem to have actually seen what I want to present later on. I will then, towards the end of this presentation, talk about statistical significance vis-a-vis clinical significance. But you're quite correct.
Well, I will let you continue, and you will answer that question as you go through. So the person that asked that question, who's from KwaZulu-Natal, may see it as it comes through, and I shall try not to interrupt you again.
Thank you very much. And if I don't answer it, please just raise the question again. And so when we are talking about the p-value, we really have to state the p-value. Let's take, for example, the p-value. If the p-value is 0.05, what it simply means is that the p-value that we have determined is right sitting on the cutoff line. And we need to be very careful when we are interpreting such a result. It could be because we have not used a sample that is large enough to establish an effect or a difference that will be determined as statistically significant. Or maybe we have used a sample that is just large enough to make sure that we reach that point where we are trying to make sure that we establish statistical significance. So that is the reason why we need to really state, if the p-value is 0.01, let us state it 0.01. Unless if it is 0.0000001, that's where we can say it's less than 0.0000. It's less than 0.01. But let me go straight to confidence intervals. So the information that we get from a p-value is the same information that we get from the confidence interval. But the confidence interval will give us additional information. So a confidence interval is a range of values within which we expect the true population parameter to lie with some associated confidence. We use the 95% confidence interval. Confidence interval is calculated from point estimates, such as the mean of a sample, that X bar there is showing mean of a sample, or a proportion which is derived from the sample, which is the P with a head there. And we want the mean, the sample mean to approximate the population mean, or the sample proportion to approximate the population sample. A confidence interval is calculated for a measure of treatment effect, shows the range within which the true treatment effect is likely to lie. I'm going to demonstrate this with a few examples. So for example, two groups, each put on different diets, and we are trying to measure the reduction in serum cholesterol being measured in milligrams per deciliter. I'll use this table as an example to show we've got population A exposed to some dietary exposure, population B, that dietary exposure. Then after some time, we measure the mean dietary, the mean cholesterol levels in population X, in population 1, and the mean cholesterol levels in population 2. Then what we observe is that when we subtract mean of the population 1, subtract mean of population 2, then in this case, we see that the two means are different by 2 digits, 2 milligrams per deciliter. Then we are 95% confident that, because this has been derived from the two samples that we have drawn from the two populations. So a sample has been drawn from population 1 and a sample from population 2. Then those two samples, we subtract the mean of sample A, sample 1, subtract mean of sample 2. Then we see the difference is only 2 milligrams per deciliter. And we are 95% confident that the true, if we had taken the entire population and this entire population, then we measure the mean for the entire population and the mean for the other entire population, the difference was going to lie between 1 and 3. And the p-value is 0.0, is less than 0.05. What it means is that there is a statistically significant difference between the mean cholesterol level in population 1 and population 2. And we are 95% confident that the value lies between 1 and 3. So this result is statistically significant. Then in the second case scenario, we see that there is a difference of 30. Let's say, if you subtract mean from sample 1 and minus mean sample 2, we see that the difference is 30. And we are 95% confident that the true population difference lies between 20 and 40. And that result is statistically significant. Case number 3, we have a mean, we have a difference of 30. That is what we observed. And we are 95% confident that the true population difference lies between 2 and 58. And it is statistically significant. Case number 4, the difference is 2 and it can lie between -2 and 4. This is not statistically significant. Then case number 5, the difference is 1 and it can range from -60 to 62, and it's not statistically significant because it's greater than 0.05. And the last one, 20, it may lie between -3 to 60, and it's not statistically significant. So what this table is showing is that if we look at case number 4, we are 95% confident that the difference can be -2, it can be -1, it can be 0. So what it means is that the dietary exposure between the two populations can actually be 0. So the difference is not statistically significant on the basis that it crosses from negative to positive. It can also be 0. So such a difference may not be statistically significant. And here, if you use the p-value criterion, if the value is greater than 0.05, we are saying it's not statistically significant. And again, here we have from -60 to 62, it's not statistically significant because it's crossing a 0. So again, with the p-value, it's greater than 0.05, so it may not be statistically significant. Then the last one, again, it is the same interpretation. It's not statistically significant because the range includes a 0. Now, then apart from showing that it's statistically and not statistically significant, the confidence interval shows of the estimate. It shows that the value, the true difference is within this narrow range, as shown here in case number 1. Number 2, the difference can be between 20 to 40. So if, for example, the reference range of LDL in blood is between 100 and 130, for example, and we want to expose these individuals under a dietary exposure. Let's say we want to reduce the dietary exposure through the dietary exposure for the concentration to be reduced by, let's say, from 200 to 60. It will be good if we have got a result like in number 2 there, because the range, the value can range from 20 to 60. For example, if we have someone who had a concentration of 100, it can be reduced by 20, so it can be 80 after that dietary intervention. But is that clinically significant? Yes, it may be clinically significant from 100 to 20, or it can be from 100 to 60. So that's a clinically significant decrease in the concentration of blood cholesterol levels. But in the first case scenario, is a decrease from 100 to 99 clinically significant? Probably not. So we may not need to change our medical interventions by changing the diet of an individual because it can reduce the levels by just 1 digit. So clinical significance versus statistical significance. In the first case, this is statistically significant, but clinically it's not significant because it can reduce the levels by just 1 digit. The second case, this one is probably both clinically significant and statistically significant. Then the third one, it's statistically significant, but may not be clinically significant because of that too, because it can reduce the levels by 2 digits only. It can reduce by 58 milligrams per deciliter. So that broad range is usually as a result of a low sample size that has been used to carry out the intervention. That has been used to come up with the calculations. Then these ones which are not statistically significant, you may not even need to have a look at them. If the sample size is large enough to establish the difference that is needed. So if there is no statistical significance like this, you need to look at the sample size that was used, whether it was powered enough to produce the difference that we would really have wanted. So confidence intervals versus p-values. Confidence intervals give same information as p-values on statistical significance. P-values simply provide a cutoff. By convention, a p-value of less than 0.05 has been agreed, beyond which we have said that findings are statistically significant. Confidence intervals are preferable to p-values because over and above showing whether it's statistically significant, they tell us the range of possible values within which the parameter can fall. A confidence interval show the largest and smallest effects that are likely given the observed data. Confidence intervals that include a 0 indicate that the treatment under investigation is not statistically significant. I think this is what we have been talking about. We need to look at the confidence interval, whether it lies within the clinical significance range or it is clinically indifferent. So clinical indifference shows a range of values of such a trivial size that you would not want to change your current practice. For example, this is statistically significant, but clinically it's falling within a range where we may not really want to change our practice, our medical practice, simply because clinically it doesn't make any difference. As I'm moving close to concluding my presentation, clinical significance versus statistical significance, it's important to know that statistical significance does not prove causation. Bradford Hill. So most of these observations that we say, this causes that there's no causation. It's just an association that X is associated with Y. Bradford Hill came up with a criterion about 9 points as a criteria to establish causation. So it's not usually easy to establish causation. So a high sample size sometimes can produce a small p-value, even though the magnitude of the difference is not clinically significant. So we saw it in our first case scenario. In this case, probably they used a high sample size, which resulted in statistical significance, but clinically that is not significant. Then conversely, a low sample non-significant difference, even though the difference is real. So a high sample size would have detected a significant difference. So the point to take home here is when we are interpreting statistical significance, we need to interpret it in context. You need to both look at the statistical significance vis-a-vis the whether that that statistical that the confidence interval falls within a clinically significant range. So clinical significance is more important than statistical significance. So this brings me to the end of this presentation. I hope I've managed to answer that question, Dr. Jackie, which has been asked by our colleague from the University of KwaZulu-Natal. Thank you.
Thank you very much, Newton. You answered it extremely well. And I think my take-home message from this is that there is a huge difference between clinical significance and statistical significance. And I think that many studies are powered to achieve statistical significance when the clinical endpoints are often not particularly important, and the attitude of publish or perish becomes totally dependent on the p-value. So Professor Aldous is going to come on shortly, and we will be asking her to elaborate a little bit more on this. But just in your opinion, if you had a p-value of 0.06, for example, and the confidence intervals were acceptable, would you not agree that if it was an important question, then we should not discount that study? We should say that this has got clinical significance. Let's just say that the p-value was 0.06, depending on mortality rate or depending on various other things that are more important possibly than cholesterol or height. You know, if we're looking at mortality rate, should we not be looking at p-values between 0.06 and 1?
Thank you very much. So, in terms of interpreting with respect to statistical significance, if it is 0.06, we say that there is no statistically significant difference. But what I want to say here is we need to establish in context. When we have one case of Ebola in Zimbabwe out of 16 million people, that may not be statistically significant. The p-value will be higher than 0.05. It's not statistically significant, but clinically it would be quite significant. The reason why, with one case of polio in the country, there is a lot of mobilization in terms of vaccines which must be available and other interventions. So, coming back to your question, when we want to interpret, to come up with medical decisions, we may not really need to stick to the statistics only. Statistics is very important. It allows us to come up with critical decisions, which we must interpret in context. So the values that we get from the statistics will be able to guide us on the next decision that we need to take clinically. I hope I've managed to answer that one.
You've answered it very well, and it goes with this another slide that I often use, which was the father of evidence-based medicine was Sackett. And he saw the p-value and evidence-based medicine as supportive of experience-based medicine and of the patient's preference. And evidence-based medicine should be the use of the best available evidence to support the experience of the treating team and the preference of the patient. And so with that, I would like to hand over to the audience to ask questions. And right, thank you for running that, Zavary. That was my fault that I cut it off too early because I cut the recording off fairly quickly. Can people hear me?
Yes.
Excellent. Hello, David. How's
Hi.
America?
Oh, it's a lot colder here than there, but it's okay.
Okay. So Dr. David Scheim has a PhD in mathematics, and he will generally speak so far over my head that I have no idea what he's talking about. But David, I know you joined a little bit late. We've just been going through, the clinical scenarios where the p-value may not be as useful as the so clinical significance versus statistical significance. And I'm going to get you and Colleen on. Colleen is also on the call. So Colleen, can you also unmute yourself as a panelist and say hello?
Hi, David.
Hi, Colleen.
So maybe I'll start with you, Colleen, because I know that you wanted to mention a paper that did have a p-value of 0.09 based on mortality. And I'd just like to hear your opinion as a research scientist and as someone who deals with p-values all the time.
I've got some competing noise. Okay.
Please give me mute.
I just want to go back to the history of the p-value. The p-value was brought into being by Ronald Fisher. We all know the Fisher exact test. He was a well-known statistician. And when people asked him, how did you decide on 0.05, or you can choose 0.1? He said, that just seemed like a really good point at where we would have certainty. It was his arbitrary decision that he knew numbers so well, he decided that that was it. And so it's become a norm, and it's a very useful norm. And it's very useful when you've got your research showing something that's a lot less than 0.01 even. But he also said that anything from 0.2 is something you should consider. So let's just put into context, what does it mean when you've got a statistical significance of 0.05? It means that you're 95% certain that that result is not by chance. If you've got 0.01, it means you're 90% certain that that's not a result you got by chance. We stand the risk if we abdicate our critical thinking to outsource it to rules and norms, that we don't think about what is actually happening with those numbers. So I'm going to mention a study, the ITEC trial it was published in 2022 by Lim et al. So if you want to go and Google it, Lim et al., the ITEC trial. Their final decision in the conclusions in the abstract said that for all pre-specified secondary outcomes, there was no significant differences between groups. That's a group that got a drug and a group that did not get a drug. And their final sentence is, the study findings do not support the use of this drug in patients for COVID-19. However, there was a difference in the mortality rate of the people who received the drug and those who did not receive the drug that had a p-value of 0.09, which means we can be 91% certain that that result was not by chance. So I think we've got to be very careful that we do not abdicate our thinking just to numbers, that we've got to think past the norms. And yes, I do believe we have to have norms, but sometimes we've got to think a little bit harder. So I hope that makes a point.
That was great. Thank you, Colleen. And I agree 100%. If I have no other option, do I want to take a safe medication that has a 91% chance of getting me better, or do I want to take nothing? And
well, the case was there's a 91% chance that you weren't going to die.
exactly.
In this paper.
So do I want to take something that means there's a 91% chance I'm not going to die? Well, I personally, and particularly if it was my children, I would choose to have that drug because I don't really care about the statistical significance, is particularly in a life or death situation or when people I love are involved. So with that, Dave, can I ask you to say a few words?
Sure. Let me just come at this from a slightly different perspective. The drugs that of decades back that we consider to be truly effective, let's say penicillin, you had like molds of bacteria growing. You put penicillin on the mold and there was a blank spot around it. This happened all the time. Essentially, the p-value of that experiment was 0.0000, you know, it was conclusive. With the cure for H. pylori, Thomas Barodi did a study. H. pylori peptic ulcers used to be intractable. There was no cure. So they did a study with a triple therapy of generic antibiotics and bismuth, where 96% of the patients were cured. So essentially, if you do the statistics on that, again, the p-value is astronomically low. So it's conclusive. Aspirin cures headaches almost all the time. So basically, drugs used to be things that worked all the time, and any statistical significance would be so conclusive that you don't even need to bother. So we're in it's profitable to make a drug that is shown to work by some way. So you can do a study of 10,000 patients. Even if the drug is marginally effective, you can say, aha, it's statistically significant. So I think, let's look at ivermectin as an example. If you look at a change in oxygen saturation of severe COVID patients, ivermectin in Jackie Stone, in your study, and 2 other studies, the statistical significance, so basically, in almost every patient, within a day, oxygen saturation was sharply improved, normalized. Versus when you had a treatment without ivermectin, nothing changed with oxygen saturation within a few days. So basically, the statistical significance of that was 10 to the -9. It was very sharp. But if you measure ivermectin efficacy in other ways in clinical studies, for example, if you look at viral load, ivermectin in many studies actually doesn't do much. What it doesn't reduce the viral load. What it does is it defangs the virus immediately. It binds to the virus and neutralizes it. So if you look at viral load, you'll see very, p.2, it's reducing viral load a little bit. But if you look at other things like oxygen saturation, then you get enormously significant p-values. So basically, ideally you want a drug where the effect is assured, immediate, and it depends on what you look at. It's best in a drug to find some quality in which the drug is consistently effective. So I guess in summary, when you measure clinical significance, look at the particular signal that can best define what's happening with the drug.
Thank you, David. That was excellent. I'm very aware of time. We had a technical glitch a little bit earlier. So I'd like to just open to the floor. I can't see any questions in the chat. that are asking, but I'll leave the Techno team to make sure I haven't missed anything. Dr. Newton, do you want to ask Dr. Shine or Prof. Aldous any questions?
Okay, thank you so much, Dr. Jackie, and thank you very much, David and Colleen, for the information that you just shared, and highlighting very important aspects with regards to the history of the p-value, as well as the information which we just received. I think it is quite helpful. I don't have any particular question at the moment that is directed to the two, but just to appreciate their coming in and clarifying some of the issues. And I also just wanted to make sure that a point which has been raised by David, quite valid, as they say that statistics does not lie, but people can lie with the statistics. When in an effort trying to demonstrate that there's some statistical significance, it's possible to just raise the sample size just to a point where people can demonstrate statistical significance. Now, as people who are in medical practice, when you are now interpreting those results, just take another look. Look at the p-value. Look at the confidence interval. Is it falling within the within a range that you interpret as clinically significant? If it is not, then you need to think otherwise. You may not need to change policy and practice because of that. Thank you very much, Dr. Jackie.
Thank you very much, Newton. And I also think that it's very important to look at clinical endpoints. So one of the, there are studies that look at hospitalization, but hospitalization is, I could put someone in hospital for observation because they've got a positive nose swab. The strong clinical endpoints are things like death. And the other strong clinical endpoints in terms of objectivity, certainly with COVID-19, is with the pulse oximetry, because it's an objective endpoint. I think we were all familiar with the Together trial, where they didn't even mention the mortality data, and they actually demonstrated a 60% reduction in mortality, despite the fact they gave it too late and they gave too little and they didn't give it for long enough. So I think we have to critically appraise. And Colleen, you have the comment that I always remember, which is we can no longer afford to outsource our thinking. And I don't know if you'd like to comment on that.
I think for many years we've trusted people to give us information. And so we've not had to think about things because we know something coming from the WHO or from the BBC or from somebody else is truthful. And we don't have time to keep up to date with everything. But I think we've learned in the last 4 years with the Trusted News Initiative and the way statistics and has been abused, and how a lot of the publications that have come out in top-ranking journals have been absolutely appalling in terms of scientific integrity, that we have to start thinking more critically ourselves. Even if we just create our own little communities of practice, we discuss these things between us. We should no longer just be blindly accepting what people say. We've got to stop outsourcing our thinking and start thinking for ourselves. And I'm not talking about independent, single people. I'm talking about us as a group, us from Africa. We've got to stay. No, this is not working for us. We're saying no more of you telling us. We want to think it through for ourselves.
Yes. And as was said earlier today in an entirely different context, we are sovereign nations. Colleen, this question is going to go to you or David. It seems that evidence-based medicine using randomized controlled trials are the be-all and end-all of making valued inferences on clinical outcomes. What about observational studies? Some conditions or situations are difficult to assess through RCTs because of the number of compounding factors, and I would add to that the failure to get ethical approval through research centers that will only give ethical approval to the studies that they wish to get through. So the real question is, how do observational studies compare to double-blind randomized controlled trials?
I think Dr. Rapiti actually has his hands up. I don't know if he's got a comment to go with his question.
Yeah, well, yeah, I think I do. In fact, I thought this question might be missed. As a frontline doctor, I'm not too very good on statistics. And as a clinician, I make my decision on whether something works by observation. And what I found was that during the COVID crisis or scandemic, the randomized controlled trial seemed to be the be-all of everything, which was, to me, was rubbish, because there were so many confounding factors. You just could not do a randomized controlled trial to say whether a drug worked or not, because somebody could be in that trial as a control and had been previously infected. So you can't say whether the drug worked with natural immunity. But take a simple thing like this. New Delhi, in 1 month during the Delta strain, used ivermectin, and in 30 days brought down the rate of incidence down to 5%. Peru, when they had the initial, had this treat and prevent immediately with ivermectin, they had a 14-fold decrease. But the minute the prime minister changed or the president changed for that province, it shot up by 13 times. Now, that was disregarded because you can't do randomized controlled trials on an entire population, but you can treat an entire population. I think, for example, in Africa, we've used ivermectin and hardly any other vaccines, and we've got the lowest rate of infection, hospitalizations and deaths compared to Europe. That to me is a kind of a randomized control, because Africa is a control, it doesn't use the vaccine, and Europe, Australia, America are the test cases of the vaccine. So I actually think this was politics more than anything else to me, relying entirely on, because it's being rather simplistic to say you're going to use only randomized controlled trials to make any particular inference. And I think we were at a great disadvantage. We were shortchanged, and lots of people could have been saved if we relied on observational studies. That's what I have to say about this. I didn't understand too much of it. I'm not shy to say so. It's really above my head.
Thank you, Dr. Rapiti. That was brilliant. David, go on to answer. I just want to mention another question that's come up in the chat, which is there are instances where we refer to single case studies and base a treatment on that, simply because nothing else has worked and another step is required. Often this produces positive results. A single case study will have no statistical significance, but speaks to doctors who don't have time to write up cases. How do we measure institutional experience, as you mentioned in the intro, from a research perspective? So the one question is the case. What about a single case report, which is a part of evidence? I think Colleen can mention that. And then David, please go ahead and answer Dr. Rapiti's question.
Okay, I mean, I wanted to focus on the Peru data, which I was involved in that study. But just in general, in principle, a randomized controlled trial, if designed by people who have no stake in the outcome, it can yield valuable information. In practice, unfortunately, and this has been addressed by scientists of the highest stature, current and past editors of leading journals, it is well known that their pharma money influences their behind the studies. They're basically, unfortunately, you can't. Let's see. The editor-in-chief Richard Horton of Lancet wrote an editorial in 2015. He said more than half of these clinical studies may not be correct. There's an enormous amount of bias. So, however, on the Peru study, so I worked with Juan Chamey, and it took 2 years really to get the paper finally finalized and accepted. But not only do we have the statistics that you cited, 14-fold decrease nationwide in excess deaths, then when ivermectin was stopped with the new president, 13-fold increase. That's exactly correct. However, we have the advantage there. Peru has 25 independent states. We have detailed data on excess deaths and on ivermectin use in every one of those states. And if you do a statistical correlation between the extent of ivermectin use and the sharpness in the reduction of excess deaths, you get a p-value of 0.002. So we have the advantage there of being able to get detailed granular data. And in this paper, we looked at every possible confounding factor, ruled them out, even social distancing. We had Google community mobility data. Nothing could explain it. So that was one case where we actually could do a solid statistical analysis and show definitively that ivermectin was effective.
Thank you, David. Colleen, would you like to reply to the case report? I mean, I know Tom Barodi's opinion is you need one Martian to prove there's life on Mars. And what it's telling you is that you need to go ahead, if it makes logical sense, and then go and study it further. So, Colleen, do you want to comment on the comment in the chat, which is coming from Lindy Mertz, I think. Yeah,
I've spoken on this forum before about evidence-based medicine and how it got broken. It was in the early 2000s that pyramid that I've shown you came about. And during the pandemic, I was using that pyramid to count the number of papers that were coming up at every level. And clearly, in a pandemic situation, you're not going to get RCTs in the first few months, but you're going to get case studies, you're going to get case series, you're going to get the observational trials. And they are important. And they were dismissed by regulatory authorities as being anecdotal evidence. So I have been fighting that with some colleagues of mine. There are 4 of us who've put together a paper that hopefully will be published in the next few weeks, where we've changed the pyramid model, which was further made bad by an arrow being put up from the bottom to the top that said quality instead of certainty. So when you had regulatory authorities standing up and saying, oh, it's only randomized controlled trials or above in the pyramid that are quality, that was a manipulation of evidence-based medicine. And quite frankly, I think David Sackett would be spinning in his grave if he had to see that. So we've changed the whole thinking to say that, yes, those case studies are very important, the case series, all of the studies. But in addition to that, the laboratory studies. We need to understand why it's working. We need to be able to understand in vitro and in vivo. So we need to look at the totality of evidence, every bit of evidence before we make a decision. And before we once again outsource our thinking to trust randomized control trials, I've never seen as many really bad randomized control trials published as during COVID-19. And I've seen really, really good case series and case studies. So the point is, I know it's very difficult for clinicians to write up case studies, but if you don't write them up, it's not going to go into the totality of evidence. And we do need to have those studies there because they provide signals. If we're going to get 10 case studies from across the globe in 2 weeks in an emergency situation, all coming up with the same thing, that's a very important signal for us to start looking at things in more depth. So yes, case studies are very important, and please take the time to write them up. You do not need ethics to write up a case study or a case series up to 3 individuals, and that's a worldwide rule. The minute you've got 4 patients or more, you need ethics. So thanks. I hope I've explained the situation.
You explained it exceptionally well. And I think, you know, most of us have been quite surprised by the fact that penicillin was approved on the basis of one case study, and we now have to have 449 studies on ivermectin. There's still insufficient evidence. And the lack of evidence of effect is not the same as evidence of lack of effect. And I agree with you with the politicization of medicine. Now, I'm very aware that it is 8 o'clock and we've run an hour and a half over time, and there are people on the call who will probably want to go off the call. So I think at this point it's a good time to stop recording. So Zachary, can we turn off the recording? Excellent. And with that, I know that Fana wanted to give a question earlier. As we all know, things tend to disappear and the internet collapses when certain words are said. So Fawn, if we stick to the word injection and the word treatment, that may be able to make life easier for you. I think the comment you wanted to make was that doctors who are on the front line are too busy to write these studies, and they're under-resourced because they don't know how to write them. And they also don't have the money and the time to actually write them, and they don't have the connections because the ethics approval go, well, you've never written a paper before, so you can't be the PI. So that's one side of the conundrum, whereas the researchers and the statisticians may not be able to see the clinical significance of why that study should be written. So the real way forward, because we're looking for African-based solutions for African problems, is to get the frontliners and the people who are making the observations to link with the researchers, such as Professor Aldous, such as Newten Handireketi, such as David Scheim. So I'd like to, Fawn, please give us your opinion, and then we'll close with maybe a quick closure from David, Colleen, and Newton, and then we'll end the session.
Thank you, Jackie. I'm sorry I missed most part of the call because of actually a colleague of mine's son committed suicide. So, but do you hear me?
Yeah, I'm sorry for that.
Yeah. So I think actually what I heard the last bit and what the previous speaker said, that's exactly what we're experiencing. And you know, when we saw the injections and people coming in the wards shortly after an injection, I always reported. You know, it was like a case report or a case study. And then when I got to 100 cases, 120 cases, I started writing to the department. They said I'm the only guy in South Africa reporting. You know, so and then when I looked at the statistics and I wrote to Dr. Crisp and everyone, I reported about, I don't know, about 15% of all the cases. So the big problem to me seems the doctors who saw but didn't take the time to report to the authorities or to the statisticians or to the researchers, or I don't know where it should go, and we should have received that, you know. So that was, and when I asked the other doctors, please send me the reports of all, you know, compilation of all your reports, and so no one reported anything to the department. You know, they had lists, little hand lists and so on, but the department said they never got anything. So I think that's big part of the blame lies with the doctors who didn't report what they saw on the notification of adverse events. And that's now where I think what you said and why I responded so immediately. We need the doctors who should have a place where those things can be reported and taken seriously. Like at this stage, I stand at 250 cases that are reported. They never responded. They never came to investigate one, because I'm the only guy reporting and who's mad enough to say there's a problem.
So Fawn, I had a very similar experience. We had 23 doctors that were seeing combination therapy work extraordinarily well. And when we came to collecting the data for the study that Colleen and David were involved in doing all the stats on, we could only get 6 of those 23 doctors to give us their data because they were too afraid, because our medical council put out a letter to everybody of those 23 doctors to question why they had been using what they referred to as an unregistered substance. But we're allowed to use substances that are not registered in Zimbabwe. If citalopram is not registered in Zimbabwe, I write something called a Section 75. High-dose vitamin D is not registered in Zimbabwe. But these threatening letters go out. And for people who've got a mortgage and kids at school and a spouse that threatens to leave them if they cause any more noise, then those people keep quiet. So I wouldn't necessarily blame the doctors. I would blame the system. And part of the system is the HPCSA, MDPCZ, HPCNA, and all of the councils that put the fear of God into the doctors who did anything that went against the narrative. So while my heart goes out to you because you did stand up, we saw exactly the same in Zimbabwe. 6 out of 23 submitted their data. And with that 6 out of 23, our p-value is 1 in 10 to the minus 9. That is 1 in a billion chance that what we saw happened by chance. It's probably quite lucky they didn't contribute any more data. Otherwise, nobody would have actually believed us with the p-value that we've come up with. So yes, doctors on the group, we would encourage you to report. But I think all of us who have reported have not been able to do so without significant backlash. And some doctors just are afraid of that. And for some of them, I mean, we're very lucky in Zimbabwe. We can't get mortgages or car loans, so we have very little personal debt. So we're much more able to say what we think. So thank you, Fawn, and I'm very, very sorry for your loss of your friend's son.
Yeah, no, it's thank you, Jackie.
Okay. So can we have a closing note from each of the speakers, and then we'll wrap it up? Newton, you get to start.
Okay, thank you very much, Jackie. I really appreciate everybody who has managed to join this call. And you raised a very important point that I've also experienced similar experiences when I was doing some routine work. I was overwhelmed with a lot of work. Not until I started embarking more into research. That's when I managed to free more time to put pen on paper and starting to analyze some of the data that we are generating on a day-to-day basis. And I think it is very important for those who are on the front line to collaborate with those people who've got the time to document what the ideas which they want to be put down in black and white. As they say, publish or perish with your experience, with your knowledge. But I think it is only ethical enough to share some of the very important observations that you as clinicians on the front line are having with patients that you are seeing on a day-to-day basis, because that is not only going to help the patients you are dealing with, but I think a number of other patients who are dotted across the globe. So the collaborations that you mentioned are really very, very important. And you can actually collaborate with those people who you wish to collaborate with. Thank you very much, Jackie.
Thank you so much, Newton. Colleen, any closing words?
Just the importance of not outsourcing our thinking. I cannot emphasize it more that we've got to start creating groups like this where we share our own thinking and debate between us and don't take everything as truth that just comes at us. And get to know your basic stats, because even the injections, we were bamboozled with statistics. So get to know the basics. Thanks.
Thank you, Colleen. And David, any closing words?
Jackie, David has excused himself.
That's perfect. I know he's got another meeting and he's in the middle of actually writing up something for Colleen, so he'd better go and get it done before she goes to bed. So thank you, everyone. I do appreciate your time. I'm very grateful to the people that remained on the call. I found it an extremely interesting call, which is why I let it run on. So, and I apologize to the Namibians because I know that stresses them out. I apologize to everybody on here for the technical glitch. We do find it easier to pre-record these sessions in case the technology does crash in the middle of the session, because it will continue to run if it's pre-recorded. And what we will try and do is edit out that small piece in the middle, and then we'll be able to share the YouTube link in the morning for anyone who wants to watch it again. I agree with Colleen. I learned a great deal about statistics from Newton, because he did take it back to basics and assume that I was about 6 years old and trying to learn this subject. So thank you, Newton. You made it very, very clear and very, very simple. And from here, we can probably take it further. But to everyone who remains on this group and is still listening, I would encourage you to understand your statistics if you are going to start arguing with academics, because the academics will just overwhelm you with sample sizes or whatever they come up with. So my solution to that is I tell them that I'll phone them back in 10 minutes, and I then phone Colleen, who tells me exactly what to tell them, and then I cut their legs out from under them, and it's very satisfying. So thank you, Colleen, for all the times you've helped me be able to argue back. And on that note, I would say to anyone, if you don't know a good statistician and a good research person, it's not a bad idea to go and sit down with someone and just really find out what the stats mean. Because a lot of people quote p-values and all sorts of things completely out of context. And ultimately, I've just been told on another group that my study that David says now on reanalysis has a p-value of 10 to the minus 9 is not considered as good as a double-blind randomized control study that has a p-value of literally exactly 0.05, which is on the fence. And while we continue with that mentality, we expose ourselves to very big pharmaceutical companies who can manipulate the statistics. And in the words of Mark Twain and Benjamin Disraeli, there are lies, damn lies, and then there are statistics. And while we laugh about that quote, it might not be quite so funny when it's affecting our clinical decision making. So thank you, everybody, for staying on for so long. We're going to shut down the chat now. Anybody who hasn't registered, it's probably too late to do so. And I wish you all a very pleasant Wednesday evening and a happy Youth Day in Zimbabwe. And we'll see you again next week for Dr. T speaking on updates in HIV from ICASA and various other conferences in the last 6 months. So, Obi, would you like to close?
Dr. Jackie, you've done a swell job in closing. Mine is just to remind colleagues to refer to the link to complete their attendance details. There is a link that's on the chat. Just put that on again for the last time. So if you can please complete the details, and once you've completed, please feel free to exit. And that's it for the night. Thank you very much, Dr. Jackie, Colleen, and Dr. Newton, and all the members that have made a contribution this evening. Thank you.
Great. Thank you, everybody. Good night.
Good night. Take care.
Thank you. Good night.